L'Hopital's rule is going to feel like we're kind of switching gears a lot here because we've been talking about all these different integration techniques. Integration by parts, trig identities that help us out, partial fraction decomposition that helps us out. And now we're going to go back to limits, which is the very beginning. The very first thing we ever learn in calculus is how to do limits. And where does this L'Hopital's rule come from? Well, it turns out we're going to find out in the next section, which is improper integrals, why we might need L'Hopital's rule. But also, at this point, we have enough foundational knowledge of the calculus to actually apply this very easy concept to evaluate some fairly intimidating looking limits. So here's the idea. If we have a fractional limit, the limit as x approaches c of a fraction, where the numerator and the denominator are both functions, f of x and g of x, and we get 0 over 0 or some sort of infinity over some sort of infinity, those are indeterminate, as we've talked about in the past. 0 over 0 could equal anything, depending on the functions. Infinity over infinity could equal anything, according to the functions. So we would have to do some sort of algebraic techniques to try to reduce it, maybe common denominators, maybe conjugates, maybe factoring to reduce, various different things. But L'Hopital's rule says that if we have this fraction in indeterminate form, then we can actually rewrite the limit by taking the derivative of the numerator and the derivative of the denominator. So that is actually a really powerful rule because we can oftentimes simplify scary-looking limits to much more simple limits. So a couple things to highlight before we move on. These are important. I need to make sure you understand these. You can't do this to every limit. The if part, the hypothesis of the conditional statement, must be true. If the numerator and the denominator both don't approach 0, or both don't approach infinity, then you can't use L'Hopital's rule, so don't try to. Okay, so don't fall into this habit that sometimes people do, is they'll say, oh, I'll just take the derivative of the top and the bottom and go with that one. You gotta make sure that the condition is met. Furthermore, you don't just check to see if it's met, you actually have to write out that condition, right? So every single time, the College Board on the AP exam will count off if you don't state the conditions before applying the rule. So that's an important thing to remember. Finally, or the other important piece is not quite as problematic. People don't tend to do this, but every once in a while I'll see someone do the quotient rule. They'll say, oh, I'll take the derivative of this fraction. Low d high minus high d low all over low squared. No, that's not it. Normally people will do the opposite, right? They'll actually do this when they're trying to use the quotient rule. And they'll just take the derivative of the top divided by the derivative of the bottom. But, you know, just pay attention. This is not the quotient rule. The quotient rule and L'Hopital's rule are not really related. They're definitely not interchangeable. So just be aware of that. So how does this work? All right, so here are some limits that we are familiar with from back in the day. First step is ask what happens when we evaluate this at -2. We get 0 over 0. Okay, that's not going to be uncommon in this section. It's something we should check, but it's not at all surprising. Our old school way of doing this would say, well, we know that x squared minus 4 factors to x plus 2 times x minus 2. The old difference of squares. X cubed plus 8 factors to x plus 2 times x squared minus 2x plus 4, the old sum of cubes. And lo and behold, x plus 2 cancels out. That was the problem because that was what was causing -2 to make us get a 0 over 0. So now we've got a new fraction that equals the original fraction everywhere except for at x equals -2. But the limit doesn't care about at the point, it cares about near the point. So we can go ahead and plug in -2 and get -4 on the top and get, let's see, we get 4 plus 4 plus 4 on the bottom. So that's going to be -4 over 12 or -1/3. All right. Great. So that's the old school way of doing it. The new school way of doing it is say, well, wait a second, because the limit as x approaches -2 of x squared minus 4 equals 0, and also the limit as x approaches -2 of x cubed plus 8 equals 0. Because both of those are met, you must write that step down. Then we know that the limit as x approaches -2 of x squared minus 4 over x cubed plus 8 equals, because of L'Hopital's rule, we'll take the derivative of the top and the bottom separately. The derivative of the top is 2x. The derivative of the bottom is 3x squared. That reduces to, well, I'm not going to bother rewriting that. It's going to be 2 over 3x. So we can evaluate that at -2 and get 2 over 3 times -2, which reduces to -1/3. So that is, of course, the same answer that we got using our algebraic method. It's another method of getting the same answer. All right, good. So going forward, we can try this with a conjugate problem. Again, if we try this direct substitution, we get 0 on the top, we get 0 on the bottom. So if we multiply by the conjugate, which is going to be root x plus 1 plus 2, then on the top, don't forget to write that limit each and every time. We don't want to offend anyone with offensive notation. In the top, we'll leave it factored, but in the bottom, we'll definitely go ahead and distribute because conjugates are meant to multiply together, right? So we've got x plus 1 times, well, root x plus 1 times root x plus 1 is x plus 1. Difference of squares, the middle terms are going to cancel out. We get -2 times 2, which is -4. Hey, that's x plus 1 minus 4 is x minus 3. What a coincidence. X minus 3 cancels out, and we end up with direct substitution into here of the square root of 3 plus 1 is 4, plus 2, or 2 plus 2 is 4. And that's fine, that's all well and good, but if we want to try L'Hopital's rule, we're going to notice from the very beginning that the limit as x equals 3 of the numerator equals 0, and the limit as x approaches 3 of the denominator also equals 0. Therefore, we can apply L'Hopital's rule. I'm not going to rewrite the original. I'm just going to say because of L'Hopital's rule, we have a limit as x approaches 3 of the derivative of the top is 1. The derivative of the bottom is 1/2 x plus 1 to the -1/2. And we no longer have the indeterminate form here. So we can do direct substitution. The 1 over 2 in the denominator turns into a 2 on the top. And then we'll take 3 plus 1 is 4 raised to the -1/2. Well, that's actually just another 1/2 in the denominator, so that's actually 2 times 2, which is 4. This last one, same idea. We're going to go ahead and get a common denominator here. This was the third algebraic technique that we learned. And we've got 1 over x plus 1 minus x plus 1 over x plus 1. So minus x plus 1. And then that's all over x. Of course, 1 minus x plus 1 reduces down to a negative x. So we've got a negative x that cancels out with this positive x. And we end up with -1 over x. Plugging in 0, we get -1, which is +1. All right. Alternatively, with L'Hopital's rule, if we take the limit of the numerator, we notice that we get 0. If we take the limit of the denominator, of course, we get 0. Therefore, L'Hopital's rule applies, and we get the limit as x approaches 0 of, in the numerator, we get, well, the derivative of 1 over x plus 1 is -1 over x plus 1 squared. And in the denominator, we get just 1. Now we can do some direct substitution, plugging in x equals 0, and we end up with -1. So we end up with the same answer. Uh-oh. I left out the negative here, didn't I? Yeah, the negative was there, and I just completely left it out. There we go. So we get the same answer regardless of which method we use.